All right, so this is page 131, question number 91, and this is a combustion analysis question. And you definitely want to do the POGL first before attempting these problems, because the POGL kind of introduces you to the process that you would go through to solve a problem like this. So it's a longer problem, so buckle up. It says one of the components that make up common table sugar is fructose, a compound that contains only carbon, hydrogen, and oxygen. So again, we don't know what the formula is, but I know it's basically that. Now it says complete combustion, which means we're reacting it with oxygen, yields 2.20 grams of carbon dioxide and 0.900 grams of water. And so I'm going to write those mass values in just so we can keep track of them. It said we had 1.50 grams of this sugar, and then it yielded 2.20 grams of carbon dioxide and 0.900 grams of water. So like any empirical formula problem, you need to figure out the mass of each element that are in that compound. So we need to find the mass of carbon, hydrogen, and oxygen. So to start with combustion analysis, you need to figure out the amount of carbon from the amount of carbon dioxide produced. So 2.20 grams of CO2. And again, we're trying to find the mass of carbon produced from this. So the first step is to convert it into moles. 44.01 grams per 1 mole. Then you're going to use a weird looking mole ratio. And it goes like this. For every 1 mole of CO2, there are 2 moles of carbon. Sorry, not 2. There is 1 mole of carbon. And I'm getting that from the formula. For every 1 CO2, there's 1 C. And then I'm going to go back to mass by doing the molar mass of carbon. So when you do that, you're going to get 0.600 grams of carbon. We're going to do a similar process to figure out the hydrogen, because all the hydrogen ends up in the water. We have 0.900 grams of water. We're going to convert to moles using the molar mass. Now here, for every 1 mole of water, there are 2 moles of hydrogen. You can see in the formula there are 2 H's for every 1 H2O. And then lastly, we get to mass using the molar mass of hydrogen. When you do that, you're going to get 0.101 grams of hydrogen. And we still need to figure out the mass of oxygen, but we do know that we had 1.50 grams of this sugar, and we just figured out that we had 0.60 grams of carbon in there, and we had 0.101 grams of hydrogen in there. So whatever's left over must naturally be all oxygen, which is 0.80 grams. So now we have the 3 values we need to do this empirical formula problem. We got the grams of each element. Now continuing on from here, we need to do our normal steps for empirical formula at this point. So again, we had 0.600 grams of carbon, 0.101 grams of hydrogen, and 0.80 grams of oxygen. So the next step would be to convert each of these back to moles. The molar mass of carbon is 12.01 grams per mole, and that's going to give us 0.0500 moles of carbon. Do the same thing for the hydrogen. 1.01 grams per mole is the molar mass. We divide that, and we're going to get 0.100 moles of hydrogen. Lastly, we convert the grams of oxygen to moles using the molar mass, and we're going to get 0.050 moles of oxygen. Now from here, you want to divide each of these by the smallest number you got, which is 0.050. Now dividing each of these, you're going to get 1 carbon, you're going to get 2 hydrogens, and you're going to get 1 oxygen. And you can see we have all whole numbers at this point, so this is where the problem's going to end for us. The empirical formula of this sugar is CH2O. Question number 93 is even longer than question 91, so like double strap in here. So it says cumene is a compound containing only carbon and hydrogen. So sounds easy so far. We just know the compound formula is CXHY. Now we're going to combust this one as well, which means we're going to react with oxygen. And hopefully you're seeing by now that when you combust a hydrocarbon, you always get CO2 and H2O as a product. Now the thing a little tricky about this problem is instead of using grams, we're using milligrams. So they tell us that we had 47.6 milligrams of cumene. We produced some CO2. Don't know what that is. And I also produced 42.8 milligrams of water. Now, just like the previous problems, we need to figure out the mass of carbon in this compound and the mass of hydrogen. And from there, I can find the empirical formula, and then ultimately the molecular formula. So let's start with finding what we know first, and that is the mass of hydrogen. Remember, in a combustion problem, all of the hydrogen ends up inside of the water. So we had 42.8 milligrams of water, and we are going to convert that all the way to milligrams of hydrogen. I want to be in milligrams, and I'll show you why in a little bit. Now to go from milligrams to grams, you are going to put 1,000 milligrams in 1 gram. It's going to cause your milligrams to cancel out. Then we're going to go from grams of water, which is 18.02, to 1 mole. So now we've converted to moles of water. Then we're going to go from moles of water to moles of just hydrogen. Remember, we got that 2-to-1 ratio like the last problem. There are 2 moles of hydrogen for every 1 mole of water. 1 mole of hydrogen is 1.01 grams. I'm running out of room. And then there are 1,000 milligrams in 1 gram. Now, when you carry this table all the way through, you should get 4.8 milligrams of hydrogen. Now, I don't know how many milligrams of carbon dioxide I had, so it's going to be hard to figure out from this how many milligrams of carbon are in there. However, the problem did say that this hydrocarbon was only 47.6 milligrams. I know 4.8 milligrams of that was hydrogen, which means the rest has to be carbon, 42.8 milligrams. So now I'm in a good spot. I've got the mass of each element in this compound, but it's in milligrams. So continuing on from here, we're going to go into our empirical formula work. I just showed you we had 42.8 milligrams of carbon in that compound and 4.8 milligrams of hydrogen in there. Now, an empirical formula question, you want to convert to moles first. Now, we got to get out of milligrams, though. So there are 1,000 milligrams in 1 gram. And then for carbon, 12.01 grams per 1 mole. So when you carry that through, you're going to get 0.00356 moles of carbon. For hydrogen, we got 1,000 milligrams in a gram. And then we've got 1.01 grams per 1 mole. That's going to give us 0.00475 moles of hydrogen. Now from here, we just going through empirical formula steps. We're going to divide both of these by the smaller of our 2 answers, which is 0.00356. And that's going to give us 1 carbon and 1.33 hydrogens. Now we don't want that. We need to get those both to whole numbers. To get these both to whole numbers, I can multiply both of these by 3. And doing so is going to give us the answer to this question, which is C3H12. 4. Now again, that's just the first part of the question. We need to find the molecular formula next. So when you find the molecular formula, you're just continuing on from where we just left off with the empirical formula. Remember, our empirical formula is C3H4. So the first step is you need to find the mass of this empirical formula. And the mass of this empirical formula, we got 3 carbons. Each one has a mass of 12.01, plus 4 hydrogens. Each one has a mass of 1.01. That's going to give you an empirical formula mass of 40.07 grams per mole. Now, in the question, it said that the molar mass of this compound is between 115 and 125. They didn't give us an exact answer. But if you remember from our previous problems, what we want to do is take our molecular formula, divide it by the empirical formula mass, and you're going to get an integer of some type. So I want to choose a molecular formula mass that's between 115 and 125, that when I divide 40 into it, will give me a whole number. So I think that something that would work would be 120. It falls within that range of the problem, and I know if I divide it by my empirical formula mass, I'm pretty much going to get a whole number from it, which is 3. Now you want to take this integer and multiply your empirical formula by it. So there's your integer. Our empirical formula was C3H4. And so when you distribute that through, you're going to get C9H12. And that is our molecular formula for cumene, the hydrocarbon that was in this problem.